All right, guys. To go along with these notions of limits and, when limits exist, and obviously we said that limits are only going to exist if the right-hand limit and the left-hand limit are exactly the same. We also have this notion of continuity, okay? So this kind of stuff in here, okay, is what you'll see in certain textbooks, okay? And then I'll show you an easier way to actually talk about. Okay, so number one, so we have this function f, and we want to know, is it continuous at a specific point? And we'll call that specific point C. Okay, number one, f of c has to be defined. Okay, so that point actually exists. Whatever f of c is, it has to be defined. Okay, and then we know that the limit, okay, has to exist. Okay, so no gaps or jumps in that graph and whatever. Okay, and then the limit has to be whatever f of c is. Okay, so you have to have a limit, and the limit has to be f of c. Okay, has to. Okay, so notice it says no holes in the graph. Okay, so I know one of the easiest ways to think about it, in your head and to visualize that, okay, is that if you could put your pencil or pen on the graph of a function and trace that function, okay, without picking up, okay, your pencil or pen, we have continuity. Okay, so I could put my pencil on that graph and I could trace it without lifting up my pencil. We have continuity. Okay, so if you have something like this, which we've seen graphs of in previous videos, okay, where if you have something like this and there is a hole removed, okay, notice I could start tracing, but when I get to that hole, I got to lift my pencil up and replace it. So this would be, okay, not continuous, okay, right here, at whatever that point is. So if that point is some c, okay, it might be continuous everywhere else, but it's not continuous at c, okay? The other problem we run into, which we've seen already, okay, is what if I have, okay, a graph that jumps, okay, jumps up, okay, does something like this. Okay, so obviously you could trace right here without lifting up your pencil or pen, but once you get here, you got to lift it up and restart. Okay, so we've got this jump. Okay, so if we say, okay, that's at some, point C, we say, okay, it's not continuous at, whatever C is. Okay, it might be continuous everywhere else, here and here, but it's not continuous at C. So notice right here, if we go back to this graph, okay, it looks like every value I choose along the x-axis, f of that is defined. Okay, no matter what I choose along this x-axis, the limit exists, and no matter what I choose along this x-axis, the limit ends up being f of whatever that number is. Okay, we're right here. Okay, notice that we don't even have anything defined here. It's a complete hole. Okay, right there. Okay, so we have f of c is not even defined. Okay, now you could even do this where I could say, okay, let's remove it and place it up here. Okay, and so that guy would be c and f of c. And you say, okay, well now f of c is defined. Yes, it is. Does the limit at c exist? Yes, the limit would be whatever the y value is right here at this point, okay, coming from the right and coming from the left. But notice that f of c, okay, is different than the limit. Okay, if I took the limit of this function, okay, it's going to give me the y value, okay, coming from the right or the left, it's going to give me the y value at this point, but the y value is up here. So it would certainly, this third sort of criteria wouldn't work out there. Okay, then right here, obviously, the second one, the limit doesn't even exist, because the limit coming from the right and the limit coming from the left are different, so the limit doesn't exist, okay? All right, now this is how I usually think about it, and I'm not saying this is bad. This isn't like this is bad, don't pay attention to that, okay? But I usually summarize it, okay? And I usually say, okay, does the right-handed limit exist, and does the left-handed limit exist, okay? If they both exist, then the limit exists, okay? And the limit has to be whatever f of c is, okay? If I'm taking the limit as x approaches to c, this limit should just be what I get when I evaluate that function, okay? That's it. So this is, I like to think of it that way. To me, I think that's a little easier to remember than all this stuff. At least it is for me. It might not make a difference for you. You might be fine with that, and I'm fine with that. I like this better, though. Okay, so we take a look here, and we ask ourselves, okay, what intervals will this be continuous on? Okay, so you take a look at that top one, and we know we have some problems at x equals 0, because obviously we're going to get an undefined value. G of 0 is dne. And so I can, quickly sketch this guy, and we take a look at it, okay? Notice that I have a vertical asymptote, okay, at x equals 0. That's a vertical asymptote, okay? And so let's see, okay? Notice that, let's see, okay? If I take any positive number for x over here, okay, I will get a negative result. And so it's going to look something like this, okay, like that. And if I take any negative number from over here, I'd get a negative divided by a negative, so I get a positive result, okay, which will look like this, okay? So if you look over here, I can start tracing that guy and just keep tracing him. There's nothing removed here, okay? So over here, that would be the interval from 0 to infinity, and it's continuous everywhere over here. There's no gaps, okay? There's no holes removed, anything like that. And then I can do the same thing here, from negative infinity, okay, to 0, okay, negative infinity to 0, okay? So notice that it's continuous everywhere other than x equals 0, okay? Because the limit as x approaches 0, okay, of negative 5 over 0, that's a dne, okay? So everywhere else is going to be continuous. Okay, so this guy, okay, my two intervals where everything is continuous would go from negative infinity to 0, along with 0 to infinity. Okay. Now we take a look at this second guy. All right, well, let's see what's going on there. Notice again, I'm going to have a vertical asymptote, okay, at x equal 1. So I'm going to have some vertical asymptote like this at x equals 1. Okay, and notice when, let's see, when x equals negative 1, okay, y is 0. So I know I'm going to have an x-intercept at negative 1, okay, 0 right there, okay? And let's see what's going to happen here. As we get closer and closer to 1 from the left, that's going to be positive, that's going to be negative. Okay, so it's going to do this. Okay, it's going to do this. Go down like this. I think I got it right. Okay, let's see. Yep, and this will be negative 1 right here. Wait a minute. Negative 1, 0. I think I have it right. Okay, I think I do. And I think this guy is going to do this. I don't know. I'd have to go back and look at it, okay, and mess around with that a little bit more. I might have it right, I might not. Okay, no. We're going to have a horizontal asymptote, aren't we? We're going to have a horizontal asymptote at leading coefficient over leading coefficient. So I'm going to have a horizontal asymptote at y equals 1. Okay, so I think this guy is going to do this and stay underneath like that, and this guy would have to do this. Okay. All right, so notice again, up here, from 1 to infinity, it's continuous, okay? And then over here, from negative infinity all the way to 1, it's continuous, okay? We're going to have this guy. It's going to do this. Okay, so it looks like I'm going to have continuity everywhere other than x equals 1. Okay, so from negative infinity all the way to 1, it'll be continuous. And then from 1 to infinity, it'll be continuous as well. Because if we look at the limit as x approaches 1, okay, of x plus 1 over x minus 1, notice we're going to get 2 over 0, and that's dne. But everywhere else, it's defined in continuous. Okay, so far so good. Let's take a look at this guy. What's going on here? Okay, so let's see. All right, well, we're working in the real number system. Okay, so we know that we would have to have radical 2x minus 3 has to be greater than or equal to 0. If it's less than 0, then we're not even in the real number system. So that would mean that 2x minus 3 has to be greater than or equal to 0. So that would mean that x has to be either greater than or equal to 3 halves. Okay, so if we have our 1 here and our 2 here, we know our 3 halves is right in the middle. Okay, and I know it's a square root, so it's going to do something like this. Okay, and obviously notice it's just a positive square root. Okay, so we take a look at, okay, there's nothing over here at all. There's nothing over here at all. Okay, so we have no graph whatsoever. And so we take a look at, okay, well, what's going on here? Hang on 1 second, guys. All right. Well, it looks like it's going to be continuous everywhere here, okay? But at 3 halves, we got a problem. The reason being is that I have a right-sided limit here, but notice there's no left-sided limit because there's not even any graph there, okay? So limit is dne, okay, as x, okay, approaches 3 halves. But once we get beyond 3 halves, everything works out. Okay, so we would just go the open interval from 3 halves to positive infinity. Okay, so we would have the open interval from 3 halves to positive infinity. Okay. And then we get down here and let's see what's going on here. Okay. Probably want to take a look at that guy in factored form and see if anything happens there. So notice that would be what? X plus 3 over x minus 3. And right here it looks like I'm going to have x plus 7 and x minus 6. So notice nothing cancels off, so we don't have holes, we have vertical asymptotes. And it looks like I'm going to have a vertical asymptote at x equals negative 7 and a vertical asymptote at x equals 6. Okay, so we have some problems here when x equals negative 7 and x equals 6 because the limit won't even exist. Okay, but everywhere in here, it'll be continuous. Everywhere in between here, it'll be continuous. And everywhere here, it'll be continuous. It'll just be a big fat no, okay, at those two vertical asymptotes. So the limit as x approaches negative 7, that won't exist. And the limit as x approaches 6 won't exist either, but everywhere else it's fine. Okay, so let's see. It would go from negative infinity all the way to negative 7. And then it would go from negative 7 to 6, it's continuous. And then we'd have to go from 6 to positive infinity. it's continuous. Okay, and that'll wrap things up. Okay, but notice right here, okay, 1, 2, and 4, it's basically, it's taken, we'll take the vertical asymptotes and just throw it out. And it's continuous everywhere else. And that happens all the time. Whereas on number 3, we have a limited, okay, domain, okay? So it'll be continuous everywhere in the domain other than an endpoint, okay? And the reason it doesn't work at the endpoint is because we don't have a two-sided limit, okay? You got a limit coming from one side, but you have absolutely nothing coming from the other side. So we say, okay, well, what do we do with that? Just throw the endpoint out, and everywhere else, okay, is continuous. Okay, that'll wrap it up for the videos this week.